everybody. In this lecture we will be discussing the use of shunt capacitor filter between the with a full wave rectifier to get the ripple free output or a pure DC. So this is the circuit diagram. You are familiar with the center tap configuration of full wave rectifier. AC mains is applied over here. This is the center tap and two diodes are used, and load resistance, between the load resistance and the two diodes, that is the rectifier output, the input shunt capacitor filter has been connected, and at the output of the load, the RL, the voltage is being measured. The operation of this circuit is now known to you. During the positive half cycle, let us draw the diagram first. This is the input voltage. So let us suppose this is the first positive half cycle. Based on this input voltage, the first diode D1 is being conducted, and the output will be replicated as same with the input. So the output will be like this dotted portion. So if this is the output voltage VO, so it will be like the dotted portion, and initially we are considering that the capacitor input filter is not present with the circuit. So what we will get for D1 to conduct during the positive half cycle, this first dotted wave, and for D2 to conduct in the negative half cycle, the second dotted wave, like this. And for sinusoidal input signal, a series of hence half sinusoidal voltages will appear at the output like this. So this is known to you. Now the peak value of the half sinusoidal voltage at the output is equal to this is the peak value. So this is the peak value. Suppose this is denoted by Vp, and this Vp will be equal to the voltage induced in the half section of the transformer secondary. That means this Vp should be equal to this voltage Vp for the first half cycle, and this voltage Vp will be equal to this as Vp. So during the second half cycle, so because of center tapping, this Vp is getting segregated. So actually if we consider this whole as Vs, so this Vp and this Vp should be Vs is equal to actually 2 Vp in this case. So now and this is very familiar to you in from my lecture on this topic in one of the previous videos. Now this will happen provided the voltage drop across these diodes are negligible and they are conducting ideally. Now when the filtering capacitor is used, now if C is now connected with this, the voltage charges the capacitor. That means the voltage that is being passed from the input side to the output by this successively by these two diodes during two half cycles, that will help this capacitor to charge up to a value that is maximum of this voltage. That means Vp. So C will be charged up to a value, peak value Vp. The charging current of the capacitor is always provided by the diodes, respective diodes. So let us assume that at any particular instant of time, the diode D1 is conducting of the circuit, and the filter capacitor is charging. This capacitor is charging through this D1. The conduction of the upper diode rather, and charging up of the capacitor will continue until the input signal attains the peak value. That means the input signal with time at some point of time will attain this peak value, and then it will start decrease. So during this so this charging will only happen until and unless it is reaching up to that peak value, the input signal. So during this charging period, the waveforms should be like suppose for this charging, what we are seeing that either of the diodes D1 and D2 should conduct. So at this along with this output voltage, let us draw the diode current, the diagram for diode current. Suppose at this point of time the diode D1 starts conducting, so the waveform will look like this. It will follow starting from here, because the diode will take a little bit time to getting the input signal at its input, to get its required knee voltage or the cut-in voltage, and from there it is following the input. The output diode current will be following the replica of the input or the output voltage. So it will be go on increasing like this up to the point Vp. This is the point Vp. So now up to near about the certain, not actually at Vp, up to near about a point Vp, and when the capacitor is charged at Vp by the natural tendency of the input sinusoidal signal, once it starts decreasing, immediately the output side voltage of the diode will be across this capacitor, that will be equal to Vp, but the input side, which was previously at Vp till the time it is reached at the point Vp, at the point peak point, after that, due to its natural course of decrease, the input side voltage will be less positive than the output side voltage, and as a result the diode will be cut off, the diode will be switched off, or it will be an open circuit. So as a result of that, there will be no further conduction of current to the output side through this diode, and the capacitor will try to remain at its peak charge Vp. Now, so we can see that at this point of peak charge, when due to the natural nature of input signal it will start decrease, the diode conduction will be stopped. So at this point the diode conduction will be stopped, so the diode current will come down to 0 once again. So the diode current will look like this. It will start from here at its cut-in voltage, and it will stop conduction at the peak voltage of the output or the input signal, whatever, both are same. At that point the diode will be cut off, or diode will be switched off, and the diode current will once again come down to 0. So this point we can say diode conduction starts, and here it stops, and this area, suppose this point is denoted by A and this peak point is denoted by B, this area AB is nothing but the area where the capacitor is actually charging, and at the point B the capacitor is fully charged. Now what will happen when the diode is switched off? Due to its natural tendency of capacitor, since a load resistor is connected in parallel with it, it will try to discharge, and this discharging will be based on the discharging time constant RL into C. This is the discharging time constant. As I have already told you in the last video, that this discharging time constant RLC will be kept quite high than the time period Tin of input sinusoidal wave or the signal, that is Vin. So because of this condition is being maintained in this circuital operation, the discharging of the capacitor through this load resistance RL will be very, very slow. In a practical filter circuit, the reactance of the capacitor is generally used here, at the ripple frequency is kept much smaller than the load resistance RL. So as a result, this C will impose a reactance that will be much smaller than this load resistance RL, So this implies the time constant RL into C will be much larger than the time period of the alternating output voltage getting from the alternating input voltage that is being applied at the input side, because this V in will immediately will provide VO, which is being drawn over here, because VO will be replicated from V in till the time the diodes are conducting, because they will be acting like a closed switch, and whatever is present at the input will be transferred to the output, and that will be replicated at the output. So both will be same, so their both time periods or frequency will be same till the time the diodes are conducting. So in this case, the variation of the output voltage becomes slower because of higher time constant RL into C in the presence of this input capacitor filter than its absence, because in its absence this question will not arise, the discharging of capacitor. So during the discharge of the capacitor, the output waveform follows an exponential curve. So this phenomena will once again, you can understand, because of symmetry of this operation, the diode conduction for D2 will once again happen at this area, between this area. So we will once again get a diode current. This is for diode current ID1, suppose this current, and if this current diode current is ID2, so this is for ID2. So because of the in the second half cycle of the input signal, D2 will conduct, and once again we will get this ID2 diode current, and as a result of that, this portion, during this portion of output voltage denoted by, suppose it is D and E, this peak point is E. So during DE, once again the capacitor will charge because of the conduction by the diode D2. So between these 2 points, that is between B and D, the diode, neither of the D1 or D2 will conduct, and as a result there is no scope of charging of the capacitor C, and the capacitor during that period can only discharge. So during this period B to D, the capacitor will only discharge. So there we will observe a little bit of dip in the curve, which will be an exponential dip or decline between the points B and D. So the output waveform should follow, so the capacitor charging discharging waveform should follow the path BD. So how the capacitor charging discharging is now looking like? AB, then BD, then once again DE. So this is A, this is B, this is D, this is E, and it will go on like this one, and once again this one. So this is the capacitor charging discharging waveform, where we can say this AB portion is used for, or is an indication of charging along with D, and this BD portion and this E, and suppose if this is considered as F, this BD and EF portion is an indicator of discharging of the capacitor. Okay. Now obviously that diode current flows during a small portion of the half cycle of the input signal, that is being shown over here, and this current is divided into will be divided into 2 parts from here. One will go through the C, and another part of the current will go through RL. One will go through here, another part will go through RL, and the part that will go through C will be helped to restore the charge that is being drained off during the non-conducting period of the diode, because during the non-conducting period of the diode, the capacitor will be in discharge mode. So the whatever charge that is being drained off during the discharge mode will be once again regained by the next immediate conduction cycle by any one of the diodes D1 and D2, during which the capacitor will only take charge. And so this is what I had to tell about you about use of capacitor input shunt capacitor input filter with the full wave rectifier. One thing I need to compare between the use of capacitor input shunt capacitor input filter with a half wave and full wave rectifier on its effect of PIV. PIV is peak inverse voltage. It is the maximum reverse voltage across any diode when it is in non-conducting state, because here in this operation we are seeing that there is a long non-conducting state for either of the diodes. So for the operation of any rectifier with a capacitor input filter at its output, the effect of its operation on its PIV is very important. So once again I repeat, PIV is when the diode is non-conducting, the maximum reverse voltage across the diode. So if we now compare based on PIV about the use of capacitor input shunt capacitor input filter at the rectifier output, we can say that for a full wave rectifier the peak inverse voltage is 2 Vm, where Vm is the peak voltage between the center tap and either end of the transformer secondary. If we consider here this is Vp actually, so in this circuit it is 2 Vp. For a full wave rectifier it is the PIV. So PIV for this case is 2 Vp, where Vp is the peak voltage between the center tap and either end of the transformer secondary. And for a half wave rectifier with a capacitor filter, the PIV is also nearly equal to 2 Vp. So what we can see here that the difference is for a half wave, this is for full wave, and for half wave it is also PIV is 2 Vp, but the difference is here the Vp is the whole, because it is actually this Vp is nothing but the whole Vs. This Vp is actually for half wave is nothing but the total voltage across the transformer secondary. This is the difference. So we can say that when filter is used, the PIV is increased for a half wave rectifier, but it is remaining same for a full wave rectifier. So we should conclude that for a full wave rectifier there is no alteration in the PIV for due to the use of shunt capacitor input filter, but for a half wave rectifier the PIV is increased. It is getting twice as much for the absence of capacitor, twice as much than the condition for the absence of shunt capacitor input filter. So we are getting benefited in terms of PIV for using shunt capacitor input filter in case of a half wave rectifier, because it is getting increased, it is getting doubled. Now let us see some other configurations. I have already told you in the beginning that the other configurations are L section and pi section filters. So let us see how it can be made. Suppose this is a bridge rectifier which is giving full wave, the output of which is connected to first a shunt capacitor input filter and then a resistor, a capacitor in shunt, then a resistor in shunt series and capacitor in shunt, 2 resistors in series and 3 capacitors in shunt. Then it is finally connected to RL, the load resistance. This is one configuration. Another configuration can be bridge rectifier. First a capacitor in shunt, then an inductor in series, once again a capacitor in shunt, then an inductor in series, then a capacitor in shunt, and finally the load resistance. So in the first case, we can say that this is an RC filtering scheme, because the filter comprised of a resistance in series and capacitor in shunt, and this is an LC filtering scheme, a inductor in series and a capacitor in shunt. Initially a shunt capacitor input filter, which we have just seen, is connected, and we can say that this is an L section filter and this is an L section filter. So this is two series connected L section filters comprised of RC, and these two are series connected L section filters comprised of LC. Alternately, we can say that this one is a pi section filter comprised of two shunt capacitors in parallel and one series inductor. So this is pi section filter, pi section RC filter, and this is along with in series with an L section of RC filter plus L section RC filter. And here, if we consider these two, it is pi section LC filter in series with an L section LC filter. So this can be different filtering schemes. Now, if we consider the RC filters, RLC are the passive components used for making passive filters, and they are often connected between the rectifier and the load resistance. But nowadays these passive filters are very rarely used to form semiconductor power supplies, but in some special applications such as audio power amplifiers, you may see this configuration of RC filtering. And in the first diagram, the bridge rectifier and with a capacitor input filter is initially shown, and along with that the designer who will design this circuit will settle for a peak to peak ripple of as much as 10% across the filter capacitor if only a single capacitor shunt capacitor filter is being used. The reason for not trying to get even lower ripple is because the filter capacitor would become too large. In that case, to get lower ripple, to get the ripples to reduce further, the filter capacitor would become larger. Additional filtering is then required, that is being done with the series cascading of consecutive filters of two L section RC filters, or we can say a pi section RC filter between the filter capacitor and the load resistor. The RC sections are always the passive filters, and in this case for RC filtering scheme, the R is much greater than reactances of the capacitor at the ripple frequency. Therefore, deliberately it is kept, the time constant of the discharging time constant of the capacitor is deliberately kept high. Therefore, the ripple is reduced easily because it reaches the load before it reaches the load resistor, and typically the R is kept 10 times greater than the capacitive reactance in this case. So in this case, R is generally greater, 10 times greater than XC. This idea, this logic will help the removal of ripples from the load resistor much more easily. So this and it will mean each section will reduce the ripple by a factor of at least 10. because of this 10 times logic of keeping the value R greater than XC. And but there is a disadvantage in RC filtering. It is because of the use of R. You know, R is a lossy component, and because of R there is always some possibility of signal loss or attenuation itself by the resistance R in its signal path, presence of R in its signal path. So this type of RC filtering scheme is unsuitable for very light loads, that means small load current, or large for in case of using large load resistance. Sorry, I have just told you the opposite. This RC filtering scheme is suitable only for very light loads, that is in case of small load currents or large load resistance, because otherwise what will happen if it is high load current, that means it will be higher loss for the signal propagation or passage through the lossy component of R. So this is all about the RC filtering scheme. The LC filtering scheme is just the opposite when the load current is large. That means RC filtering scheme is used for lighter loads, and LC filtering scheme is used for heavier loads. That means when load current is larger. So for large load currents it is always an improvement, and in this case the idea is to drop the ripple across the series components, and in this case due to the use of inductors, you know that the inductors will pose low reactance to the AC signal as much as the frequency is lower. In other words, as the frequency is increased, more and more signal reactance for by the inductors will get increased. So just on the contrary to the use of capacitor in the signal path XL, the inductive reactance is j omega L. So as much as the omega is increased, so more and more AC signal is being passed through the inductors, the inductor will pose a high reactance to the signals that will block the signals as much as the signal frequency is higher. So the DC is very well passed through the inductors, but the ACs are blocked. So that's why the inductors are always connected in series. That means they will pass DC easily up to the load resistance, but they will block the AC from going into the load resistance or in the output, on the contrary to the operation of capacitor, which is preferred to be connected in parallel or shunt. Because of this same idea, because for capacitor it is Xc equal to 1 by j omega C. It is inversely proportional, the capacitive reactance, unlike the inductive reactance, which is directly proportional. So by making inductive reactance much greater than the capacitive reactance, we can reduce that will make the ACs should be better blocked by the inductors than the capacitors in the signal propagation path in series with the load resistance RL. So we can in this way reduce the ripple to a very low level, and the DC voltage drop across the inductors is also much smaller than it is across the RC combinations, because inductors are not that much of lossy component like a resistor, because the winding resistance of the inductors are generally chosen very smaller, and that's why the LC filter is very popular than the RC filtering scheme. But still nowadays the LC filters are becoming obsolete in typical power supply applications because of its size and cost of the inductors, which are generally higher. So inductors is also having size and cost problem for making the filtering scheme for different power supplies, and hence for low voltage power supply application, the LC filter has been replaced by ICs. ICs are used for filtering scheme, and one extra added benefit of ICs being used in making the power supplies for filtering purpose is that it should be providing us the regulation also. That means the regulation of voltage. So that is another added benefit for using ICs in power supplies to get the filtering scheme. And these ICs are containing diodes, transistors, resistors and other components in a very miniaturized package, so that the size and cost problem is also reduced, as in case of LC filtering scheme. So now let us see IC voltage regulator as well as the filtering scheme. A small diagram like this, like the previous one: AC source, bridge rectifier, at the output of bridge rectifier a shunt capacitor filter is being connected, and that is directly connected to a filter cum regulator which is called IC voltage regulator, which is doing filtering plus regulation things, and then the load resistance is connected at its output. So this IC voltage regulator will is an integrated circuit made up of diodes, transistors, resistors and other components. That means in some cases active devices also. Not only it is dependent on the passive devices for its making, the ICs for this purpose, and this device not only reduces the ripple, that means it not only helping us to reduce to do the filtering purpose, but also it holds the output voltage constant at a particular level, thereby the regulation is achieved at the output of the rectifier along with the filtering scheme. Later we will be discussing in some different classes, in some different lectures about this filtering as well as regulation scheme. That is, we will discuss this IC voltage regulator separately in a different class. Thank you.